Hello, U13s. How's it going, guys? Okay, so last lesson we looked at Born-Haber cycles and the webinar kind of broke down. I was having issues with my microphone, so I'm going to take a second run at Born-Haber cycles, but I'm going to do it in a slightly different... I was having issues with my microphone. There we go. So I'm going to take a slightly different approach to it. I'm going to be looking at this purely from an exam-style question perspective. And then what we can do is we can draw all those connections back to what we did in the previous one, even though I know there were lots of issues with the sound. Hopefully we'll be able to get out of it everything that we need. Okay, so I'll crack straight on. So let's share my screen. And then I'm going to switch my camera over to my clip cam. There we go. But I'll leave my audio on my laptop. Yeah. Okay. So there we go. So learning objectives, switch my tablet into tablet mode. There we go. Right. So second lesson or second go at Thermodynamics lesson 2, Born-Haber cycles. So my learning objectives for today's lesson is be able to draw Born-Haber cycles, define each step and understand each step within it. So last lesson, I'm just going to do a really fast review on what we looked at last lesson. The key facts that we took away. I don't like, guys, if you want me to leave the learning objectives up, you can. I can. I'll put the facts next to them. In fact. So we've got facts. So last lesson, the first fact that the first takeaway point was this is all about ionic. This is all about ionic compounds. We realized that Hess cycles are focusing on covalent, whereas Born-Habers are focusing on ionic. We then saw we had the definition list. This is because each step in the ionic compound formation has its very own enthalpy definition. We remember that the definitions from thermodynamics all start with the heat energy change when 1 mole of, or the enthalpy change when 1 mole of, depending on which one you like. And we'll see more of those today, especially when one's coming up on question number 1. So you've got to learn this list because they're going to ask you probably 1 or 2 of them in every paper, and you just have to know them. Bear that in mind. The last part of the whole process was really us trying to tie everything together in a cycle, and that the cycles are energy profiles. A Born-Haber cycle is an energy profile. And we picked up that if the arrows, energy profile, so if the arrows go up, that's going to be endothermic. And if the arrows go down, then it's going to be exo. Negative delta H, exo. Because this is an energy profile. And then we're going to apply our rule of Hess cycles that we've seen before about kind of walking around the cycle. So define the term electron affinity for chlorine. So they've actually put us in a context here. The first thing I'm going to do in this question is I'm going to write the equation that they want me to do. So they're saying chlorine, 1 atom of chlorine gas, gaining 1 electron to form 1 ion of chlorine gas. So that's the equation that they want, because electron affinity is gaining electrons, whereas ionization is the losing of electrons. Please remember that they are the opposites of each other. So I'm now going to put this into words. So I'm going to say the heat energy change when 1 mole of chlorine atoms, 1 mole of chlorine atoms, I'm going to color code this, 1 mole of chlorine atoms gains 1 mole of electrons to form 1 mole of chloride ions. And then we do the usual finishing process, all under standard conditions, constant pressure, all under standard. You do not need to say under standard states because they're not in their standard states. Although they are in this case because chlorine's a gas anyway, but they'll ignore that. All under standard conditions, which is constant pressure. And we're done. 2 marks for that definition. And you can actually get the first mark simply for writing the equation. The last mark comes from the heat energy change in 1 mole level under standard conditions. So that's your second mark here. I really love, there's the second one. And it used to be worth 3 marks, but they're slowly reducing it in numbers, saying that, you know, if the definition isn't complete, then it could only be 1 mark. Okay, the next thing is we now pick up our first Born-Haber cycle. And at this point, when I said I was going to take this from an exam question perspective, it's nice for me to show you the exam question immediately. Complete the Born-Haber cycle for magnesium chloride by giving the missing species on the dotted line. Include state symbols where appropriate. The energy levels are not drawn to scale. Right, so what I'm now going to say is my first learning objective of being able to draw. Yeah, drawing a Born-Haber cycle. Fritz Haber and Max Born, a Born-Haber cycle. So the way that I teach this is what's called the frame method. Line, 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 line. There you go. That's it. Line, 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 line. So this is called the frame method. And the way that I do it is baseline, ceiling, 3 on the left, 1 on the right. This is called the frame method. Now, some teachers don't like the frame method because the frame method, we're going to deviate from this at various stages. But what you can always do is you can use, because a lot of the time, the most common statement I hear from students is, I don't know where to start. I don't know where to start. And what I realized was if I teach the frame method, they've always got a place at which they can begin. And then you can edit it as you go. So for example, this one fits the bog standard sodium chloride model. Yeah. And this delta H is always the delta H of formation. And on the first shelf on the left goes our 2 substances that we need to form that salt. Then what we're going to do is we're then going to walk around the cycle and get everyone to the position that we need them. We need to get each of sodium and chlorine, you need to get each one of them to the point where they can go into an ionic salt. So the first thing that we need to do is we're going to focus on sodium until it's done. So we're going to take the sodium and we're going to turn the sodium into a gas. Step number 1. This is the enthalpy of sublimation or enthalpy of atomization, whichever one you want to call it in this case. Yeah, now we're not finished with sodium yet because we know that, by the way, the whole point of the vaporizer or the sublimation is to get me from a metallic solid to a gas, which means a single atom. Yeah, I've now got a single atom. Now what I need is I need the ion. So I'm going to now ionize sodium, delta H ionization energy 1. So I'm going to now form sodium 1 plus gas and its electron. Right now, chlorine makes an appearance. I'm now going to just put chlorine on here because so far chlorine has done absolutely nothing. And I want you to note where I've put the arrow. I have been putting these arrows here. Number 1 is they're both endothermic. And I've put them above the sodium so I know who I'm dealing with. Most of the time when you get given cycles, the arrows just kind of go at the side or in the middle. Sometimes you just see the arrows running up directly through the middle like this. And what they're doing is they're trying to test you on your ability to understand what's going on. So in this case, I'm focusing completely on sodium until it's happy. Now sodium at this point is done. Do the metal first. Yeah. Now what we're going to do is we're going to now deal with chlorine. Now chlorine is currently in a pair. So what I need to do is I need to rip chlorine apart. So now I have chlorine as an atom. Yeah, chlorine before was in a pair. I had half a mole of the pair, but I now need to split her in half. So this one's going to be delta H atomization because I made 1 mole of atoms, or half the delta H bond dis. They love that one. That's something to bear in mind. Now I've got chlorine on its own. I still need to put sodium up there because sodium hasn't done anything, but he still needs to be included in the steps. And now I'm going to continue to focus on chlorine. And now what I need to do is what I'm actually going to do is I'm going to put that right in the middle. I'm going to put sodium 1 plus its electron with state symbols, and I'm going to put chlorine over there as an atom. Now what I'm going to do is I'm going to focus on turning the chlorine into chloride, and it's going to gain the electron that sodium lost. This, of course, is the delta H of electron affinity 1 for chlorine, EA1. And, of course, the sodium remains on the shelf unchanged, and the electron, of course, now vanishes. Now, at this point, we get this final arrow, which is the delta H of lattice or the delta H of lattice, either one. We always deal with formation in chemistry. We can do lat form if you like, but they probably won't call it that. They'll probably just call it the delta H of lattice. So, and that brings me to the end of my cycle. Now, that is the basic cycle. 3 shelves on the left, a base and a roof, 3 shelves on the left and 1 shelf on the right. So this is the frame method. It's very handy. I'm actually going to show you how this often deviates, though, by showing you another one. So here is Born-Haber number 2. Born-Haber cycle number 2. So before, this Born-Haber cycle was focusing on sodium chloride. That was this guy. Let's do something a bit more challenging. Let's do magnesium bromide. That's an interesting one. So the first thing I'm going to do is I'm going to frame it. 1, 2, 3, roof 1. And I'm going to put magnesium chloride on the base as a solid. Right, first thing I realize is that the first shelf is always the enthalpy of formation. I need magnesium as a solid. I need bromine in a pair this time, but bromine's a liquid. So I'm going to have to deal with that on a separate step. So the first thing I'm going to do is focus on magnesium. I'm going to first of all turn magnesium into a gas. Yeah, bromine remains unchanged, untouched. Oh, sorry. Next, not finished with magnesium. What I now need to do is I now need to ionize magnesium, but the problem is it's ionized twice. So I'm going to get magnesium 1 plus gas, and this is going to be the enthalpy of ionization energy 1. This one here is the enthalpy of atomization or sublimation, depending on which one you want. And the bromine, again, remains unchanged to liquid. I'm not finished with magnesium yet. I'm going to add another shelf because I need Mg2+. This is going to be the enthalpy. This is the delta H of ionization energy 2 for magnesium. I've now got 2 electrons on the shelf. I missed my electron on the other one. Electron, there we go. And then bromine still remains there as a liquid, unchanged. Now my magnesium is ready to go. The magnesium now matches what I need for the salt. The next thing I'm going to do is I'm now going to focus on bromine. Now the first step I need to do with bromine is that I need to turn it into a liquid. So Br2 liquid. This is the enthalpy of vaporization, delta H vap. Delta H vaporization. And magnesium, of course, has been ready, but I haven't changed it since the last one, so it becomes this. What I now need to do is I now need to smash the bromine up. So I'm going to make a better roof on this one. So the magnesium remains unchanged. The magnesium is ready to go for my ionic solid, being a gas, and it has 2 electrons waiting. But now I've got to split the bromine up. Why is it magnesium bromide if it's MgC? Thank you. Somebody who's paying attention. Thank you. Sorry, Haber. Thank you, Emma, the only one paying any attention. There we go. So the bromine became a liquid. Now I need to split her up. And I'm going to get 2 bromine atoms now at this point. Sorry, and that shouldn't be a liquid now. That would be a gas because I vaporized it. Thank you. Now that one there is going to be the enthalpy of bond dis, 1 mole. The heat energy change when 1 mole of a bromine-bromine bond is broken to form its constituent elements all under their standards or all under standard conditions. We're outside of standard state, so they will ignore it if you write it. It doesn't actually matter about that, which is hilarious. You shouldn't be able to write that. If you write that, they should have Dr. Mark, but apparently they don't. But we could have also times 2 delta H atomization alternatively, because we're forming 2 atoms. So we'd have to do, that'd be 2 moles of atoms rather than 1. So it'd be delta H atomization times 2. Now we need to give bromine those electrons. So what's now going to happen is I'm going to have the delta H of electron affinity for bromine, and the bromine's going to be Br-, but I've got 2 of them, and each one of them, that one has to be multiplied by 2, and then the magnesium remains unchanged and the electrons disappear from the equation, from the shelf, because they're now balanced. And then we have our lat form and lat dis. So you can clearly see I'm adding in shelves where needed. Now, drawing a cycle from scratch is actually relatively unusual for Red Excel. They do it about 1 in 5, but most of the time they will give you a cycle that's already been built. And what they're going to do is ask you to complete the labels, which is far, far easier. So in this particular case, complete the Born-Haber cycle for magnesium chloride. So first thing is, we realize that magnesium has definitely changed here. Yeah, we've got a change in magnesium. So the first thing I've got to realize is I've got to add chlorine gas to this in a pair unchanged. And that chlorine gas will also be there unchanged as well. The next one is we've now done ionization energy of magnesium number 1. So this now becomes +1 electron. I'm going to shrink my pen a bit here. Yeah. So this is going to be +1 electron, and the chlorine again remains unchanged. And then the next one is ionization energy 2. So now we've got 2 electrons. Wait, sorry. What exactly is the definition of for lattice energy? Is it like breaking all the bonds? Be careful. If you say, okay, good question. So the lattice energy. So lattice energy immediately means formation. If they don't say lattice, then it automatically means, if they just say lattice, so definition of delta H lattice, lattice enthalpy, yeah, that one there, you're immediately going to assume formation. So this is the heat energy change, or enthalpy if you prefer, heat energy change when 1 mole of, heat energy change when 1 mole of, ... an ionic solid, 1 mole of an ionic solid is formed from its constituent ions, all under standard conditions. Constant pressure. Standard conditions. There you go. And the equation would be Na plus gas plus Cl minus gas goes to NaCl solid. So that's the equation. I hope that helps, Ria. Good question. Glad you asked. And that's the enthalpy of the lattice. We immediately assume formation. Unless they say the word dissociation, we assume formation. Okay, so we're now creating this. The next thing is, now that we've got magnesium 2+, the chlorine still remains unchanged. What we now realize is there has been no change now between the magnesium. What that means is the next step is going to be chlorine. So this one's now going to, the 2 electrons still remain, but I now have 2 chlorine atoms. Now that's going to be 2 atomizations, or 1 bond dis, depending on the data they give us. So the next thing is, right, what's now going to go on the other side? Well, the 2 electrons are now going to disappear. Ooh, definition. I know, but it's not as bad as you think. Once you get to grips with them, like, it's okay. It's not as bad as it seems. Once you've got the routine, it works. So we're now going to have 2 chloride ions as a gas, and the electrons now disappear from the equation. So, and this one, by the way, is delta H lattice, because the arrow is pointing down. It's exothermic. And exothermic means we're forming bonds. Right. Now, the next part of the question is that they now give you the data. They now give you the data, and they say, use the Born-Haber cycle, just going to highlight this, use the Born-Haber cycle in table 1 to calculate the value for the electron affinity of chlorine. So what they want for us to find out is this guy. That's what we're looking for. Yeah, and I'll label that. So this is what we want. So this is our end point, and this is our start point. What we're now going to do is we're going to take all of this data over here, and we're going to throw it into this picture. So the enthalpy of atomization of magnesium, so that's down here, that's plus 150. And then, so I can tick that one off. Enthalpy of atomization of chlorine, oh, that's clever. That's here, that's plus 121 there, but that's for making 1 atom, and I'm making 2 atoms, so I'm going to multiply that step by 2. Next, the first ionization energy, take that one off, first ionization energy of magnesium, that's going in here at plus 736. Next, the second ionization energy of magnesium is 1450 plus. Notice that they're all endothermic and that they're going up. That makes sense as well. We're okay with that one. Next, the enthalpy of formation of magnesium chloride. Oh, formation, first arrow, goes down here, minus 642. And then the final one, lattice energy of formation, minus 2493. So what we're now doing is we're now going to use our cycle just like we did in a Hess. This is the most important arrow I can ever teach you. Okay, I'm going to make this nice and big. So here is where we start. So we are going to start here, move all the way around, and come back to the finishing point. So up, down, across, and up. Right, so we're going to start at the same point, start here, end here. Right, so now we can create an equation for this. So, and this one now just follows the usual routine. So my delta H question mark equals, so this bit here equals this root here. And now we just follow the usual rules. So this arrow here, the very first arrow at this point here, I'm trying to highlight this one here, is going against me. I am moving in this direction. I sometimes prefer doing this rather than, I sometimes prefer doing that in my arrows than anything else. And what I'm realizing here is this one here is coming down and that one is going up. What that means is it's going to be minus. So this one is minus brackets plus 1, 2, 1 times 2. Whoops. 1, 2, 1 times 2, close brackets. The next arrow is against me, minus brackets plus 1450, close brackets. Next arrow against me, minus brackets plus 736, close brackets. Next arrow against me, minus 1 bracket plus 150, close brackets. Next arrow, it's with me, plus brackets, minus 642, close brackets. Do you always deal with the metal first? No, you don't have to, Dana. Hang on, maybe this defeats the whole point of the cycle thing, but does it matter what order the shelves are in? Like if you wanted to atomize chlorine before magnesium, or is it just convention, I guess? Not like other girls. That's weird. Do you always deal with the metal first? Is this so that we can do the exothermic electron affinity at the end? That's a really good question. Yes, it is. So the electron affinities always do come last. Yeah, these ones always come last because they're going to be on that side of the cycle. But you can do them in any particular order you like. And in fact, they've rejigged them at times. You could end up doing that. Your cycle would look a bit wonky donkey. Yeah, so if you did this, let's do something like, let's go crazy. Is this so that we can do all the exothermic electronic? Yeah, kind of rare, yeah. Let's do something really cool. Let's do, I'm going to do, oh, okay. Yeah, let's do something we know. Let's do lithium, I don't know, bromide. So we could do, the first shelf is always delta HF, delta H of formation, lithium solid, and bromine as a liquid. Bromine 2 liquid, and we need half of it. Right, if you do the bromine first, your cycle's going to look all wonky donkey, that's all. So if we do the bromine first thing I'm going to do on this shelf is I'm going to split the bromine in half. So I'm going to do Br2. No, sorry. I'm now going to end up with just Br. Oh, sorry, we've got to vaporize it first. So we're going to have lithium untouched, say symbol, plus half Br2 liquid. Then we're going to split it up to make Br2 as a gas. Sorry, that's a gas there, folks, sorry. And then Br gas. Yeah, so this one's delta H VAP. This one is delta H atomization would be better, but they're probably going to give me bond enthalpy, which means I need half the delta H bond dis. Half bond dis. And then if we then do the next one, we'd have to extend this arrow outwards so that we could then drop down here to do, oh, hang on a sec, we can't. There's no electron to collect yet. That electron's come out of nowhere. So no, you've got to do the ionization first to provide the electron for the electron affinity. So there you go. There's why. Came out in the wash. Isn't that fascinating? You can't do it because the equation would be unbalanced. Or each shelf in the process must be balanced for atoms and charge. So there you go. You can't do it first. You do the metal first because it's going to provide you with the electron that will allow you to make it negative, because otherwise the shelf won't balance. That's really neat. I like that. That's fun. That came out in the wash. Never had anyone ask me that before. Thank you very much for doing so. It's a great question. Great question. Right, so now guys, now that I've created my equation, I'm going to put that into, now I know that the mathematicians in the room are going to freak out because I'm just going to type that in exactly as it is on my sheet. I make less mistakes than you do. Times 2, close brackets, minus brackets, plus 1450, close brackets, minus brackets, plus 736 brackets, minus brackets, plus 150, close brackets, plus brackets, minus 642, close brackets. And I get an enthalpy of electron affinity. Isn't that fascinating? Oh, wow, this is really, really high. Oh, I've missed a bit. Guys, I've missed a bit. It's easy. Sorry. I've missed the last step because someone asked me a question. So the last arrow is going against me. So minus brackets, minus 2493, close brackets. Right, so I can just take my thing and go minus brackets, minus 2493. Go, close brackets. And that gives me a final answer of minus 727 kilojoules per mole. Now, I've made a mistake, and it's deliberate because it's the realization that this here is the delta H of electron affinity times by 2. And they've done this on purpose. Technically, you could still do ionization of lithium before bromine. Technically, you still could, but you do the, yes, you can, Dad. Yeah, but then you can't do the ionization without the sublimation of lithium first, because you can't remove an electron from a solid. It must be a gas, which means you must have completed the lithium process before you can even tackle the bromine anyway. Anyway, so this now needs to be divided by 2. So the final answer divided by 2 is exactly what the realms I would put it in, which makes total sense. There we go. Minus 363.5 kilojoules per mole, and I'm done. So they're not as complicated as they seem. They're doing exactly the same thing. This is a year later. Figure 1 is a Born-Haber cycle for potassium oxide. Now I need to talk you through this one because there's an additional step which you need to understand, and that's this one. Okay, so I think what I'm going to do is I'll look at the question itself. We'll go through it, and then I'll explain the step when we get there. So it just says complete the cycle. So the first thing is we're forming potassium oxide. We know that this one is the delta H of formation, and this one's going to need the elements in their standard states. So potassium's a metal, it's a solid, plus O2 gas, and you need a balance for it. 2 potassiums and 1 oxygen. There we go. First step done. Next, deal with potassium first. So what we're now going to do is we're now going to have the delta H of sublimation times by 2 because I have 2 moles of potassium. So I'm going to have 2K gas plus half O2 gas. Haven't finished, by the way, it could have been delta H of atomization times by 2 as well. Could have been that as well. So the next one is we now need to ionize potassium. So we're going to end up with 2K pluses gas plus 2 electrons on the same shelf. Goes to half O2 gas. Right. So now this is delta H ionization energy IE1 times by 2. Right. The next step is we need to split oxygen up. So this one's going to be delta H atomization because we are making 1 atom. Alternatively, we could do delta H of bond dis divided by 2. Yeah, half of bond dis because I'm only making... Yes, but the order should not matter. The cycle will still flow. Yeah, but the charge won't balance. The charge always has to balance. It always has to be negative on all the shelves. Because E are just showing the charge in empathy. No, that's not correct, actually, Dat. That is not true. They're actually there to balance for the charge. The cycle must balance for charge and atoms all the way through the process. That was part of the understanding. That was part of the realization. I think that Born and Haber got was realizing which processes must be happening first. The bit that really boggles your noodle later on is the fact that you realize that the energy is required to break all of these bonds, and the energy is supplied from the formation of the ionic solid, which the ionic solid doesn't come until way later. So you're expending a huge amount of energy before the formation of the cell happens to give you the energy to do the original processes. How bonkers is that? That's why they have a high activation energy, because it's needed. Isn't that cool? The energy has to come out of the collisions at the beginning, and then it's supplied by the enthalpy of lattice, which is enormously bigger compared to all the rest of the bits anyway. It's why it's exothermic. Right, the next one, the arrow comes down. This one here is as normal. This is electron affinity 1. So this is delta H. This is delta H, electron affinity 1. And this is exothermic minus delta H. It's exo. We wrote that down in the last thing. That was one of the other facts, which was one of the other fact number 4 up here. Fact number 4 is all delta H electron affinity 1s are exothermic. Are exothermic because we are forming, an electrostatic attraction, forming an electstat attract / bond between the electron and the positive nucleus. Between electron and positive nucleus. Positive nuke. Yeah, we're forming an electrostatic attraction. We're making a bond. It's exothermic. But here's now the really tricky bit. Charge will if you change the order. Yeah, okay, Dat. It's just easier to do this. Yeah, just Dat, stop arguing with me and shut up and just do what I'm telling you to do. So now we're following by electron affinity number 2. Now this one is now going up. It's endothermic. And they commonly ask this, exothermic, they commonly ask this at A level. It's a super common question. So the question here, explain why E electron affinity 2 is endothermic. It's endothermic. Why is it costing me energy? Now the reason being is answer. I'll do the answer in green. Answer is that the first ionization energy for oxygen, you're adding a negative electron to a neutral atom. So there's no repulsion. So when you form, and by the way, I shouldn't do that. I should actually show you a bit of scale on size here. The oxygen is now going to balloon. Yeah, we now have this picture. It's gained an electron. Yeah, fully 1 minus. Yeah, this had 6 electrons previously. Oh, sorry. Continuity, please, Mr. Duncan. Yeah, so it had 6 electrons originally, and now it's gained an electron over there. And there was no repulsion between the originals, but we're forming this attraction over here. So that attraction is what releases the energy, minus delta H. But in the second electron affinity, in IE2, we're going from a fully negative ion, yeah, and we're trying to get it to gain another electron. And what that means is you now have a huge amount of electrostatic repulsion. And this is the answer, electrostatic repulsion. And it's way more repulsive than the energy that's going to be released from the bond itself. So you now, by the way, it's going to become even larger, balloons even bigger. Let's try and do that a bit better, Mr. Duncan. There we go. It gets even larger at this stage because we know that when you gain an electron, you increase in size. There's more electron-electron repulsion within the outer shell. Now, this is massively endothermic. Yeah, there we go. This is endo, positive delta H. And the reason being is that the repulsion is much greater than because we are still making an attraction. We're now making this attraction here. But the exothermic value provided by that attraction is way smaller than the endothermic repulsion over there. So overall, the first process, of course, must be exothermic, but the second process is always endothermic. Sorry, the first one's exo and the second one is endo. And they love this question. It comes up so often. We might actually see it in this particular example. Okay, so this one's now endothermic, and we're also going to have to multiply that one by 2. Both of these, oh no, sorry, we don't. We actually only apply them once because there's only one atom of oxygen. So now, if you notice, the last arrow in this cycle is a dissociation. This arrow here is actually a dissociation because the arrow's going up. Is it like the first ionization energy, second ionization energy, but the other way around? No, because the first ionization energy, no, it's more, it's got more to it than that, Dana. Because if you do the first ionization energy, if I have, let's say, aluminium, yeah, if I have aluminium and I remove its first electron, yeah, and I rip it off, it's going to shrink in size, becoming Al1+, yeah, and an electron, and that's going to cost me energy. That's going to be, I'm breaking an electrostatic attraction between the electron. I'm breaking this attraction here. Yeah, I'll do it in blue because I'm going to have to break it. So it's endothermic. And then if you go to the next one, yeah, the next one I'm going from aluminium 1+, yeah, and I'm removing a second electron. It's going to shrink again to form aluminium 2+ and 1 electron. That's going to be much more endothermic. Yeah, we know that the amount of energy to ionize these grows exponentially. We saw it in magnesium, 750, then jump into 1400. The next one's going to be even higher, of course, for aluminium because it's the last one in the shell, and the fourth one even higher than that. So these we know that ionization energies, one compared to versus ionization energy 2 versus ionization energy 3, etc., we know that these values will always increase. They're always endothermic, but they are increasing from 1 upwards. We know that. This is why we get our ionization energy graphs, which we often do this, and we go, what group was my element in? And you go, it's in group 2, because the first 2 elements were in the outer shell, and there's an enormous jump, because we've now entered a shell closer to the nucleus. So these are the outermost, and that's the shell further in. But they're always, of course, moving in a singular direction, whereas this one is very much the opposite. One's endo and one's exo, which is rather odd. Right, so now that we got to this point, they now give us the data, and we need to apply this data into this cycle. So, and they're asking us to calculate lattice dissociation. So this is this question here. Highlight the question. This question here is that one, and we're going to start here. This is our start point, and this is our end point in the question, because that's the direction of the arrow telling us that. And then we're just going to apply the numbers to it. So the enthalpy of atomization of potassium. So they've given us this one this time. So I'm going to add that data in there, plus 90, but we need to multiply it by 2. Next one, tick that off. The first ionization energy of potassium, which is the next one, plus 418, but we need to times it by 2 because we had 2 potassiums. Take that one off. Next one, the enthalpy of atomization of oxygen. Yeah, okay, which is this one. Yeah, which was perfect. We don't need to multiply it by 2 in that case. So the value for that one is plus 248, plus 248. And then we don't need to multiply it because we're making 1 atom in this case, and atomization states 1 atom. So that one's done. Then we can tick off, then we can say, right, first electron affinity for oxygen, that's this guy over here. So that's now should be exothermic, which it is, minus 142, put it in a bracket. And as you only need to times it by 1, don't need to multiply it at all. Next one, electron affinity 2, which now becomes plus 844 in a bracket. And then the last one is the enthalpy of formation, going down here at minus 362 brackets. So now we can create our equation for this. Yeah, so our question mark, most important arrow in any Hess cycle or Born-Haber, we travel from the start, across, and up, and across. Well, actually, I prefer to go and across until there, then down, then across, then up, then across, and then down. Oh, don't need to do that though because we've ended. Right, so now we can just apply this. Let's create our equation for this. So the question mark equals start at the same point, start down here. And it's going, I'm moving in this direction and it's doing the opposite. So this is going to be minus, that means going against me, minus 362, close brackets. This one's here is with me, plus brackets, plus 90 times 2, close brackets. This one's with me, plus brackets, plus 418 times by 2, close brackets. This one's with me, plus brackets, 2 plus 248, close brackets. There's no multiplier for that one because it was atomization. Then on to the next one. This one's going with me again, plus brackets, minus 142, no multiplier needed. Next one, this one's going with me, so this becomes a plus, brackets, plus 844, no multiplier needed. And then that brings us to the end. Type that directly into our calculators, exactly the way it is. Yeah, minus 362 plus, close brackets, plus brackets, plus 90 times 2, close brackets, plus brackets, plus 148 times 2, close brackets, plus brackets, plus 248, close brackets, plus brackets, minus 142, close brackets, plus brackets, plus 844, close brackets. And we get a value of plus 2,328 kilojoules per mole, which makes sense for such a strong electrostatic attraction between a K plus and an O2 minus. That's very, very endothermic. And that actually also makes sense that it's positive because we're starting with the ionic solid here and we're ripping it apart in the dissociation, rip apart to form its ions, its gaseous ions. So a huge amount of energy will be needed, which makes total sense. Remember that the calculator doesn't show you that positive, but you need it because you're telling them it's endothermic. So that completes that question over here. Explain why the enthalpy of lattice dissociation of potassium oxide is less endothermic than that of sodium oxide. Oh, that's quite nice. So they're saying that the lattice dissociation of potassium oxide, so I'm going to rip that apart and form K plus gas and O2 minus gas, that's positive delta H because it's endothermic, we're breaking bonds, is less endothermic compared to sodium oxide. So we're going to rip this apart. They're saying it's less endothermic, so that's a bigger endo, and we're going to form sodium 1 plus gas and O2 minus gas. So what would be the difference here? There's only one difference. So the first thing is to realize that the negative, the anions are the same. So if I draw those anions on there, they're the same anion, but they have different cations. And the cation here for potassium is this big, and the cation for this side is this big. We know that the sodium ion is smaller than the potassium. And what we learned in ionic bonding at AS level is that the charge and the size of the ion matters. So what you're going to write down here is bullet point number 1, the sodium ion, the Na plus anion, is smaller compared to K plus ion. 1 mark. Next one. The electrostatic attraction, I always worry when a message appears on my thing because it means there's probably something wrong with the sound. That's what I seem to have learned from all of this various gubbins. It's all good. Sorry, guys. The electrostatic attraction between K plus and O2 minus is weaker than Na plus and O2 minus. Yeah, because the size of the ion is larger, therefore a weaker attraction, therefore less energy to break apart lattice. Break apart K to O lattice. And we're done. So I hope you found the questions useful. I feel like this was a really good way of doing this. We've had a look at some really good chemistry here. It's really, really nice. And we've done 2 Born-Haber cycles. And I do feel like at this stage, I can tick off each of these and say, you can draw them, you can define them, and you understand each step. So I definitely think this has been a much better lesson than the previous one. So I'm going to end my lesson there today, and I will post your homework, guys, on the Google Classroom. Your homework is just going to be doing a series of exam questions on Born-Haber cycles. I have just taken them directly out of papers. I've chosen 4, and I will post those on the Classroom, and you can do those for next week, and then I will post the mark. I'll go through them next lesson. And then we're done with Born-Haber cycles, and we move on to the perfect ionic model. We'll pick up PIM next lesson. I'll see you guys all soon. Have a good rest of the day. Bye, guys.